Hi, Jameson Tutorials. In this session, we look at limits and we are focusing mainly on limits at infinity. As you can see here, there are some graphs of base functions which we are going to be considering, because in this first part, we'll be looking at limits at infinity for polynomials. In the first case, we have linear functions. You can see that as x tends to positive infinity for this other graph of y equals x, as x tends to positive infinity, y tends to positive infinity. So if we were to get the limit as x tends to positive infinity of x, the answer would simply be positive infinity. And it is just like substituting or plugging in positive infinity in the function. So that will be done. It applies in some cases. We pretend as if we are substituting it, although infinity is not a number. Infinity is just an idea that expresses a very large number. And so we can't really perform algebraic processes on it as we do with ordinary numbers. But then sometimes we need to simulate that process of substituting it in order to quickly get what is happening. So it's important to know. It is also important to know that infinity can be a large number. It can also be a very large number. It can even be a very, very large number. So there are cases where you need to look at that in order to determine whether your limit would be what type of answer, whether it should be finite or positive infinity or negative infinity. So this is the result here. If I now take the limit as x tends to negative infinity of x again, from the graph, I see that as x tends to negative infinity, y tends to negative infinity too. And this is then negative infinity, which again is simply obtained by substituting or plugging in negative infinity for x. You'll still get this. On this other side, if you take limit as x tends to positive infinity of negative x, this is the graph of negative x. As x tends to positive infinity, y tends to negative infinity. And so this answer will be negative infinity, which is simply also considered to be just plugging in or substituting positive infinity in the function. The infinities or the negative sign would appear in the answer. And so that is how you can also get that limit. If we take the limit as x tends to negative infinity of negative x, we go to the graph again. As x tends to negative infinity, y instead tends to positive infinity. And so the answer is positive infinity. If you go and substitute negative infinity directly in the function, you will still get this answer. So it's important to know. The graph helps you to really see what is happening, but as a quick way of getting it when you arrive in the exam, for example, as you're solving, plugging in will be faster. Now, for polynomials generally, your limit to infinity will always give you some infinity, be it positive or negative. And so that is the general trend that you'll be doing. The graphs are just there to help you see what is actually happening, but when you arrive these cases, you just plug in the value of infinity, be it negative or positive, and determine what sign. What is important in plugging in is to determine the sign of the infinity. The answer is already infinity whenever you are dealing with polynomials. But you will now need to look carefully and see if it will be positive or negative infinity. Concluding this way, if I were to make a transformation of any of these base curves, either by shifting it upwards or downwards, I would not change any of these values, because if I shift upwards, the behavior of the curve towards positive or negative infinity will not change. The inclination or the gradient of the curve still remains as it is, and so going this way towards positive infinity, I will still be having y going towards positive infinity, and the same for this way. So we can conclude that limit as x tends to plus or minus infinity of x plus or minus any constant would still give the same infinity sign. If it was positive, it will be positive, and if it's tending towards negative, it will also be negative. In this other case, if I again take limit as x tends to positive or negative infinity of a positive or a negative number minus x, so it's still a transformation of this one, shifting it up or down would not change the orientation of the graph, and so its behavior towards positive and negative infinity will not also change from the one of the base graph. It will still be the same. And so this one, generally we saw that when it tends towards positive infinity, we have but negative infinity, and when it tends towards negative infinity, we have but positive infinity. And so that is what happens. Overall, we can then conclude that if we have positive infinity and we add a number to it, it remains positive infinity. If we have positive infinity and we subtract a number from it, that would still give us positive infinity. It is a large number. Adding some small number to it would make it still very large. And you see now, this is a large number and this is a very large number. Infinity is not a number at all, because it can be a large number, it can still be a very large number. Now in this other case, we have positive infinity minus some small number, and the fact that it's very large, subtracting a small number doesn't change it from being large. This is still very large and then large, as we can see, but it still gives the notion of infinity, and so we write this. Other cases to note involve the fact that if I have again negative infinity and I add a number to it, it wouldn't change from being largely negative. If I have negative infinity and I subtract a number from it, it wouldn't change it from being largely still negative. It becomes more negative, more largely negative, and so these are the signs. Then infinity plus infinity is actually positive infinity, and the reason is that a large number plus another large number gives another very large number, which still gives the notion of positive infinity there. But it wouldn't be the same for subtraction. When I have infinity minus infinity, it is really indeterminate. This large number and this one could be the same, and it could give me 0. This large number and this one could not be the same. This one could be very large and this one large, so I will instead have positive infinity. This one could be small or large and this one very large, and it will give me negative infinity. So this one actually is indeterminate. In the case of infinity times infinity, we have a large number times another large number, so we can still have positive a large number. And negative infinity times negative infinity, that could give us, or that would give us positive infinity. A large number times a large number gives another large number. So a negative large number times another negative large number would make it positively large. So these are the arguments we need to put. With this one, we can conclude that infinity, positive infinity squared gives you positive infinity, and negative infinity squared gives us positive infinity. And this can be extended to higher powers. If I have positive infinity raised to an even or an odd power, I would still get positive infinity. Negative infinity raised to an odd power, I would get negative infinity. So negative raised to an odd power will remain negative. If it is positive infinity raised to an even power, it will remain positive infinity. Negative infinity raised to an even power would become positive infinity, because negative raised to the power 2, for example, is positive. Raised to the power 4, for example, is still positive. Okay, in the case of quadratic functions, when x tends to positive infinity, y tends to positive infinity, and when x tends to negative infinity, y still tends to positive infinity. So we can say limit as x tends to positive infinity of x squared is simply positive infinity, and limit as x tends to negative infinity of x squared is still positive infinity. And this one actually is like plugging in positive infinity squared, which still gives you positive infinity, which we already predicted here. And in this other case too, is plugging in negative infinity and squaring, which will become positive. So the graph shows us all the arguments that we have put here. It confirms it. Alright, so take note. In this other case, limit as x tends to positive infinity of negative x squared should be, if I move towards positive infinity, as x moves towards positive infinity, y moves towards negative infinity. And so again, we see here that it is simply a plugging in that has occurred. Negative into positive infinity squared. If you square a largely positive number, you still get another large positive number. So, but the negative sign makes it to be negative infinity. And limit as x tends to negative infinity of negative x squared. If you look at the graph again, as x tends towards negative infinity, y tends towards negative infinity too. So, which can be obtained directly there as simply negative into negative infinity squared, which negative squared becomes positive, and so that is positive infinity in the bracket when you square it. And this gives negative, and this gives positive infinity when you square negative infinity. The negative sign makes it again negative infinity, and the graph confirms that. Alright, so this notion can then be extended again to the case where you have a quadratic function. Suppose I have limit as x tends to 2x squared plus 5x plus 4. Let us say as x tends to positive infinity. This is simply a transformation. This particular quadratic function is a transformation of this one. There is a stretch and there is also a shift, be it to the left or to the right. It doesn't change the behavior of the curve towards positive and towards negative infinity. So when you arrive here, then simply consider the main term, which is the determining term. The term with the highest degree is what determines how the curve would behave towards positive infinity. And so we could just say limit as a form of shortcut as x tends to positive infinity is simply that of 2x squared. Ignore the other smaller terms. And this could then be obtained by simply plugging in positive infinity, which should give positive infinity, because squaring positive infinity, you have positive infinity. Multiplying 2 by positive infinity still makes it to become positive infinity. It's like doubling a very large number, you still get a very, very large number, and which still gives the notion of infinity. If I instead had limit as x tends to negative infinity of, let us say, x squared plus 6x minus 2, again I will look at the main term, the determining term, or the term that really determines what is happening at infinity, which is the base function of the transformation actually. And so again the shortcut would be just to take limit as x tends to negative infinity of x squared, plugging in negative infinity and squaring, which gives us positive infinity, and so on. So that is what you'll be doing even with higher degree polynomials. Once you have limit as x tends to something like x to the fifth, or as x tends to positive infinity of x to the fifth plus 3x minus 5, I simply go to the main determining functions and then evaluate. That gives limit as x tends to positive infinity of simply x to the fifth, which gives positive infinity to the power 5. And we don't have any worry with that. It gives a very large positive number, which is positive infinity. And if I had limit as x tends to negative infinity of another polynomial like x to the fifth, or negative x to the fifth this time, plus x squared minus 5x plus 6, again I would be interested in the bigger, or the term with the higher degree, which gives me limit as x tends to negative infinity of negative x to the fifth. Plugging in negative infinity, we get negative into negative infinity to the power 5, and negative raised to an odd number remains negative. So this will be negative of negative infinity, which is positive infinity. And to confirm all these things that we have talked about polynomials here, let us look at the graph of y equals x cubed and that of y equals negative x cubed. As x increases towards positive infinity, the graph of x cubed increases towards positive infinity, and this is positive infinity, which could be obtained directly by plugging in again positive infinity and cubing. Largely positive number cubed gives another very large positive number, so the notion of infinity again comes in there, and so on. So if I instead took limit as x tends to negative infinity of x cubed, I would get again, I go back there, as x tends towards negative infinity, y tends towards negative infinity too. And so it's like plugging in negative infinity in the function and evaluating. Negative raised to an odd power gives negative, and so the answer will be negative infinity as confirmed from the graph. On the other side, if I take limit as x tends to positive infinity of negative x cubed, I would get from the graph, as x increases infinitely in the positive direction, y decreases infinitely in the negative direction. And so we would be talking of negative infinity. And if you were to do a direct plug-in, you would still get that answer. Let us see what happens there. If we put negative into positive infinity and cube it, we will still arrive negative infinity. You cube a large number, you get another very large number, and you negate it, it gives you a negative large number. So the notion of infinity comes in again, which is negative, and so on. So it confirms again what we are just from treating here with higher powers. And so generally, when you get now as the conclusion limit as x tends to positive or negative infinity of any polynomial, just take the higher degree term and do the substitution. So if I had 5 minus x squared plus 4x to the fourth, I would simply say equals limit as x tends to plus or minus infinity, whatever sign it will have, of mainly the term that determines it, which is 4x to the fourth, the term with the higher degree, and that gives us 4 into plus or minus infinity raised to the power 4. We will just be left with positive infinity as the answer.